Good morning, everyone, and welcome to the thrilling event where we unveil the latest chapter in SCIA's remarkable journey, SCIA Engineer 25. As I stand here today, I can't help but feel a surge of excitement about the incredible year we've had and the bright future that lies ahead. Today, this is our second big release event this year. Just a few months ago, we launched SCIA Engineer 24, which was one of our most successful releases ever with the highest and quickest adoption rate. Now, we're back with another groundbreaking version, SCIA Engineer 25. But that's not all, because earlier this year, we announced our merger with Allplan, marking the beginning of an exciting new chapter. At Allplan, we're revolutionizing workflows and building bridges, offering a complete ecosystem that covers the entire design-to-build workflow. This merger isn't just about combining companies or products. It's about bridging gaps between workflows, between design and construction, between different stages of a project's lifecycle. For you, this means seamless integration, enhanced collaboration, and a more streamlined process from concept to completion, ensuring that your project's deadlines are met. Now, let's dive into SCIA Engineer 25. This version embodies our commitment to unifying precision and performance, packed with powerful and advanced tools to help you tackle all types of projects more efficiently. We've implemented a new harmonic analysis that pushes boundaries. This allows you to save significant time by performing an analysis for an entire frequency range at once. Plus, you can now design more accurately using not just nodal harmonic loads, but also linear and surface loads. This means more precise vibration analysis for complex structures like bridges or high-rise buildings. Building also on the construction stages that we introduced in version 24, we now enable you to perform code checks in stages and, as well, an exciting new feature that we have the possibility now to conduct a stability analysis for every single stage. This ensures your designs are safe and compliant at every phase of the construction, reducing risks and potentially costly errors. We've also made major improvements to our 3D wind engine, changes that will allow you to do more accurate wind load calculations on your structures, including new types of structures like canopy roofs. And for our users who use US standards, SCIA Engineer 25 brings the latest updates for AISC 360 and ASCE 7. This ensures your designs are always up to date with the most recent code requirements. And what if I tell you that you can now link analysis and steel detailing? Thanks to SAF, our structural analysis format, you can now export and import steel structures between SCIA and SDS2. SDS2 is part of our Allplan portfolio as well, and is specialized in steel detailing. This integration streamlines your workflow, reducing errors in data transfer and saving you valuable time in your steel projects. And for more accurate concrete column design, for example, we have integrated SCIA Engineer with our solution Freelo B5+. This will allow you to design your columns even more accurately than ever, taking into account fire design. And this is just a glimpse of what's new. There are many more exciting new features that my colleagues will tell you all about in a few moments. As we celebrated recently SCIA's 50th anniversary this year, we're not just looking back, we're looking forward. We're excited about the possibilities that lie ahead as part of the Allplan family, and we can't wait to explore them with you. Thank you all for being here today. We have an exciting program lined up to show you how SCIA Engineer 25 can transform your work. Let's dive in and discover the future of structural engineering together.
Good day, everyone. I'm Michele, Director of Customer Success here at SCIA. It's my absolute pleasure to welcome you all to our online conference today. Our theme for this conference is Unifying Precision and Performance, a baseline that truly encapsulated our commitment to delivering accurate, efficient, and high-performing solution to all of you, my dear engineers. Firstly, I'd like to express my gratitude to Jad for that wonderful introduction. It is always a pleasure to hear from my friend and Director of Product and Customer Success. Now, allow me to give you a glimpse of what we have in store for you today. We're excited to introduce you the latest feature of SCIA Engineer 25 presented by Marco, our product manager. His knowledge and dedication to product development will surely provide valuable insight into what's new and exciting in our software. Following his Marco presentation, Merit, our customer service engineer, will provide a live demonstration of SCIA Engineer 25. Merit's expertise and practical approach will help you understand the real-world application of our product. Later on, we also hear from Nigel, our product director for cloud, who will be discussing about Beam Plus and Autoconverter. Throughout our conference, we encourage you to engage with us. Please feel free to ask questions in our chat. Our team of SCIA experts will be answering them throughout this conference or directly to you later. We will also have a Q&A session at the end of this conference where most of your questions will be answered in real time. Once again, thanks to all of you for joining us today. We hope that this conference will provide you with valuable insight and tools to enhance your work. Let's look forward to this fruitful and engaging session together.
Good morning everyone, and again welcome to the SCIA Engineer version 25 release conference. In this presentation, we'll be diving into the improvements and the new feature which will be released in SCIA Engineer version 25 this week, and we are excited to share this content with you. Before starting seeing the new feature, allow me to mention that, as usual with SCIA Engineer release, you will find in SCIA Engineer version 25 improvements for all construction sectors. Either you are working with residential buildings or with non-residential buildings or with civil structures and bridges, you will find in this release features and improvements that touch each one of this field. So let's enter into the core of the presentation and start with the new features and improvements related to the analysis field. In what concerns the analysis, in SCIA Engineer version 25 there has been a large work done on features needed for accounting the effect of human and machine-induced vibrations. As you know, buildings or civil structures like bridges and in general every kind of structure can be affected by vibration that can be induced by several sources. First of all, human activity in buildings or passage of pedestrians in bridges, but also machines like pumps, motors, fans, rotating machines. This vibration can have an effect of discomfort in buildings, but can also have a structural impact when they pass a defined result. These phenomena are particularly important in buildings with composite and lightweight floors and are particularly relevant for footbridges also. In order to account for these phenomena, so to study them and prevent their bad effect, we introduced in SCIA Engineer version 25 new harmonic analysis capabilities. The new analysis allows the user to perform single frequency and frequency range harmonic loading analysis. It means that the user can perform the analysis for a given frequency, but also specify a frequency range by minimum, maximum frequency and frequency step. So the analysis will be performed at once with one click for all this frequency, and the result will be encompassed in an automatic class that will be generated. Also, there is the possibility to consider in-phase and out-of-phase loads in order to consider the most complex harmonic phenomena. There is the possibility to apply harmonic loads under the form of nodal loads, line loads, and surface loads. And there is the possibility to use constant and Rayleigh damping. Also, there is this new feature that is the possibility to automatically apply the sign of the harmonic loads based on a modal displacement, so based on the eigenshape. This feature can be particularly interesting for situations in which the user want to pose himself in the worst case scenario, that is the one in which the harmonic loads is orientated following the eigenshape that is closely spaced with respect to the resonance frequency of the structure. This kind of situation is specified in many guidelines for design of footbridges or buildings. How it works, this feature is very simple. The user just applies simply his harmonic loads, like for instance this constant harmonic loads that is applied at once as surface loads on this deck, and then he selects in the menu which eigenshape he want to use for the load signature and in which direction this signature should be done. And doing so, the sign, so the direction of the load, is automatically applied based on the shape of the eigenmode. As you can see in this picture, where the eigenshape goes in the negative side, the applied load is negative. When it goes to the positive side of the z-axis, the applied load is positive. Again, if I would have used another eigenmode like this one, the application of the load would have followed. So the load would have followed the direction of the eigenshape. And so the worst case scenario is automatically taken into account just with a click, without the need for the user to specify different zone of loads with positive and negative sign. Many of you probably know that harmonic analysis was a feature already present in all the 32-bit version of SCIA Engineer, but you probably noticed that the new solution offers many more possibilities with respect to the old one, so it's really a big step forward in the dynamic analysis for SCIA Engineer. So next to harmonic analysis, another feature concerning the analysis that has been introduced in version 25 is the possibility to perform stability analysis on stages. So this is an extension of construction stages analysis that allows the user to do what? It allows to select one or more construction stages and specify that in these selected stages the user wants to compute stability. So to perform a buckling analysis. Why to do that? It's because there can be the need during a construction sequence to show that the structure is stable not only in the final stage when it's finished, but during the whole construction process. And these new features allow exactly to do that, and in a very simple way, just selecting this checkbox, everything will be automatically computed. And finally, what concerns the developments for the analysis part, a new convergency graph for nonlinear analysis has been introduced in SCIA Engineer version 25. As you know, we had this convergency graph in past version of SCIA Engineer. We introduced a new one that not only gives the information for every selected nonlinear analysis, but also has many more features, like for instance, the information about the amount of load that is applied. For instance, in this picture you see here, in the third increment there is 60% of load that is applied, in the fourth increment there is 80% of load that is applied. This information can be very useful for the user for the case in which the analysis stops, because he knows quickly, just looking at this graph, which percentage of the applied load the structure was able to sustain. But there are also other interesting features, like the possibility to export this graph in Excel, or the possibility to select each one of the points of this graph and have the local information. So with this feature we complete the part relative to the analysis, and let's move now to see the new features and improvements that have been introduced in the fields of results. The first of these new features is the introduction of the new dynamic detailed results menu. This new results menu serves primarily to extract value relative to accelerations, velocities, and displacement of the structures. It's a feature that can be used for all kinds of dynamic analysis in SCIA Engineer, so either seismic response spectrum analysis or harmonic analysis. There is the possibility so to visualize this information on the screen, to export that in PDF, or also to have that in Excel format. But there are also other possibilities offered by this feature. First of all, the possibility to select which kind of results one want to extract, if are peak results, so the maximum value, or root mean squared results. As you know, the root mean squared results can be very useful to judge about comfort of slabs. For instance, are the value in which the threshold are expressed in most of the guidelines.
Hello everyone,
There is
thank you
also
for
the
joining us
possibility
today.
to select if
We are just
one
about
want
ready to
have
get
results
started with
just
our
in the
conference.
geometrical
We are going
modes
to wait
defined in
a
SCIA
few
Engineer,
minutes
or
to
in
allow
all
everyone
different
a chance
element
to
modes
join.
of the mesh.
We appreciate your
Results
patience
can be
and we are
extracted as
excited
for
to share with you what we
superposition,
have in
but
store.
also for single eigen mode, so for the single eigen shape I can have results of acceleration, velocity and displacement components. And there is also the possibility to extract this new feature that is the detailed modal table. What is this? It's a table that can be given as Excel format or as PDF format, and in this table there is an extended format of the output of modal analysis. This feature is primarily intended for all the user that needs to do advanced post-processing of dynamic analysis through third-party software or by hand calculation. And it allows, for instance, to compute flow response spectra or other sophisticated output. Next to this, there is the introduction in SCIA Engineer version 25 of the possibility to visualize stress results on single tendons. As you know, it can be very useful for the people that do pre-stressing analysis to be able to check for each single tendon which is the state of stress. And in SCIA Engineer version 25 we introduced these possibilities that was missing before. And finally, in what concerns the results, there is this nice improvement that has been introduced in the engineering report, that is the possibility to do an edit of multiple live pictures at once. In the specific, now it is possible, differently from before, to change the viewpoint of multiple pictures at once. So the user just need to select in the engineering report all the pictures for which you want to change the viewpoint, and just with a single action the viewpoint will be changed for all the picture. And similarly to this, there is the possibility also to change the view parameters for multiple pictures. So selecting multiple pictures at once and changing the view parameter. This also is a very powerful feature. So for what concerns results, I stop here. And let's move to the new features relative to the loading. In what concerns loading, in SCIA Engineer version 25 there are several novelties in what concerns the 3D wind load engine. First of all, is the possibility to apply the wind load on canopies through the force coefficient approach. As you know, till now was possible to apply wind force on canopy roof through the pressure coefficient approach. But as you probably know, the Eurocode is clear and it says that in order to apply the wind force on canopies, they can be applied through the coefficient of pressure approach when the purpose is to design the roof element itself, but when the purpose is to design the structure, the wall structure, the overall force coefficient approach should be used. And in SCIA Engineer version 25 we introduced this possibility, so the user has just to select in the setup of the wind load which kind of approach you want to use, and the software automatically will determine the equivalent line load or the pressure loads accordingly. Next to this, there has been a change in the algorithm in what concerns the overlapping zones on the roof. For instance, if we have a look at this picture, we can see that the Eurocode is not really clear, because on the corner it's not clear which pressure should be applied, the pressure of zone B or the pressure of zone C. Till now we were just adding this force, so in this corner zone there was an overpressure that was leading to anti-economical design. Starting in SCIA version 25, only the most unfavorable pressure between these two is selected, as it is recommended by many national guidelines. Finally, In what concerns the 3D wind load engine, we introduced the possibility to take into account for the friction forces induced by the wind. Your code on this point specify a criteria in order to judge when the friction force should be used. This criteria looks at the ratio between the surface of the structure that are parallel to the direction of the wind over the surface of the structure that are orthogonal to the direction of the wind. This criteria can be quickly satisfied when dealing with elongated structures typical of industrial halls. And for this, we introduced this simple switch that is present in all the wind data. And when the user just select this friction force switch, he has only to specify the roughness of the surface, that can be the roof surface or the wall surfaces, and automatically the software will take into account also this component and will generate the friction force over the envelope of the structure. And finally, in what concerns loading, the last development introduced on this field in SCIA Engineer version 25 regards how the temperature load is managed in combination for bridges. Indeed, to properly account for temperature loads in bridge combination, a distinction has been added between uniform and gradient temperature loads, and moreover, now these two different temperature loads are combined together according to the relative chapter of the Eurocode. So there is not anymore the need for the user to manually assemble combination for taking into account this phenomenon of temperature load, but now everything is managed automatically. And now let's move to the final part of this presentation that is related to the novelties introduced in what concerns design in SCIA Engineer version 25. First of all, again, on top of construction stages analysis, it has been introduced the possibility to perform design checks on stages results. What means? It means that for each stages or for all stages at once, the user can perform design of concrete, steel or timber. This was a possibility that was not offered before and it can be very useful for the people using construction stages analysis. Then, next to this, there has been the introduction in SCIA Engineer version 25 of the AISC 36022, that is the latest design code for steel in US. This feature can be very useful not only for the people that design structure in US, but also for many users that are based in Europe and design structures worldwide, because the AISC code is used not only in US but in many parts of the world. So, starting SCIA Engineer version 25, there is the steel design and check according to these American norms, and as well there has been introduced the load combination rules relative to the ASCE 722 for American code. Next to this, there have been several improvements concerning the update of the American profiles in the library of cross-section, the update of the Brazilian profiles in the library of the cross-section, and as well new L-type of section has been introduced into the cross-section library. And finally, for the design part, there is now in SCIA Engineer version 25 a new link with freeload modules, that is the B5 Plus modules, that is the module of freeload that regards the design and check of columns. This module can be very powerful and important for the SCIA user because it allows, between other, to perform fire design and check of reinforced concrete column, possibility that for the moment is missing in SCIA Engineer itself. So, with this feature, I end this presentation of the novelties of SCIA Engineer version 25. I hope that you enjoyed it and you found a feature that you were looking for. And in the next presentation, my colleague will show you more in the detail some of this. So thanks for your attention and enjoy the rest of the presentations.
Thanks Marco for the enlightening presentation on the new features of SCIA Engineers 25. We have now here Bjorn and Gino who help us answering some of your questions. Gino, I start with you. With this new feature, which one do you think is the most important for the daily work of structural engineers?
I specifically like the new improvements in the 3D wind load engine, like the friction forces, and also the improvements in the engineering report. These things were asked by many users, and now they have them.
Thanks a lot, Gino. I agree with you. Bjorn, it seems a lot of attention in the presentation was paid to construction stages in the development of this new version of SCIA Engineer. Can you share with which construction segment will especially benefit from this improvement, and for which type of structure this approach is needed the most?
Yeah, sure. I believe that different construction segments will benefit from this new development. For example, the multi-story buildings, where you will be able to do the analysis and also the checks for each stage of the construction. On the other hand, you also have the civil structures, like bridges, and there, especially with the stability analysis, which will be possible to run for a specific construction stage, which will give you a better insight in the behavior of the structure.
Definitely. So this will help a lot our users. And now, after we thank Bjorn and Gino that will come back later for our Q&A session, and we go further with the merit presentation on the new features of SCIA Engineer 25.
The first topic we will present today is the construction stages, specifically focusing on the design and checks. As you may recall from last year, construction stages was reintroduced, allowing you to model and analyze structures with construction stages. Following this year, the full workflow is enhanced to include concrete design and checks. Let us take a look into a model together. This example contains two different models. One will be a standard linear calculation, while the other one will be a calculation with construction stages. This model on the right consists of 10 different stages, while the standard model on the left is fully added in the last stage. In this example, we also utilized material modifications to enable the creation and analysis of the structure with a different timeline and varying concrete properties. In particular, first level 1 will be cast. 7 days later already, level 2 will be cast, and so on. This means that when level 2 is cast, the characteristics of level 1 are not yet the same as when the concrete is 28 days or older. By creating these material modification groups, the changes in this E-modulus are taken into account. Here we can review the different modification groups for each stage. As you can see, once level 1 reaches 28 days, 100% of the E-modulus will be achieved. However, at each stage, there are still other levels that haven't reached 28 days yet, and their E-modulus is adjusted accordingly. The correction that is taken into account can be found in the material modifications. The E-modulus reaches 60% after 7 days, 90% after 14 days, 95% after 21 days, and 100% after 28 days. For each level found in this model, we created a different type of material to apply this correct information to each level. When we take a look into the cross-section library, you will find different cross-sections for both beams, columns, and transfer beams. Apart from these three types, which are used in our standard model, for the construction stages, multiple cross-sections are created. These cross-sections will have exactly the same size and parameters, but for each level, these are duplicated. By doing so, the different materials for each construction stage can be applied accordingly. Now we run the analysis to take a look into the results of both models. We start with the resultant of reactions to take a look into the self-weight of the structure. A name selection is used to take a look into the results for each model separately. For the left structure, construction stages is set to none and the load-case self-weight is selected. Now that we know this result, we can compare this with the construction stages model. The name selection is switched, the property construction stages is set to all stages, and we see now that for the construction stage analysis, we find exactly the same result for the reaction forces. Now that we know the self-weight is the same, we can check the different internal forces. We use a name selection to take a look into the result of a transfer beam in both models. We change the construction stage to all stages, and this result will immediately show you that the internal forces in the transfer beam are different between both models. In the model with construction stages, we notice higher internal forces. Now we can take this a step further and take a look into the new development, the reinforcement design of this transfer beam. For these results, we will use exactly the same named selection, and we change the construction stages to the last one. For the extreme 1D property, we change the value to member, so we are comparing the most extreme numerical values of both members. As we now expect, in the construction stage model, more reinforcement is required. The classic workflow of concrete you are used to is available here, which means we can take a look into the required longitudinal reinforcement as well as into the required shear reinforcement. Apart from that, you can also take a look into the provided reinforcement that will follow the template that is defined for the members. In these results, you find a different reinforcement scheme as well for the model with the construction stages. Additional reinforcement is added where necessary. When comparing this to the standard model, you will see that for the standard linear analysis, no additional reinforcement was required. For this provided reinforcement, we can of course also take a look into the different values. For example, you find the weight of your longitudinal and shear reinforcement as well as your shear reinforcement configuration here. For these results, we see something similar. When taking a look into the output options, you will find that the detailed output, which you are used to, is also available for the construction stage analysis. This report will give you an overview of the full concrete beam check. It will be performed for both the beam in the linear analysis as well as for our construction stage model. You can find here all the necessary information you need to take a look into the required reinforcement as well as into your reinforcement template. After reviewing this, you can choose to convert your reinforcement to real bars, and we can take a more detailed look into our transfer beam of the construction stage model. We will start by taking a look into the ULS check for this transfer beam. As we did before, to check this result, we change the type of selection and we make sure that the construction stages are taken into account in this result. Once these are loaded, we can check if our design is sufficient based on all these ULS checks which are activated. In this case, this seems to be fine, so we can take a further look into both the ULS and SLS checks. So we make sure that these are activated here on the right if you want to perform them. We will include the crack width check. Once these are loaded again, we can check the results. And in this case, we do notice that for the crack width check, in some locations, the check is not sufficient. If you want, you can take a further look in the standard output, where you get an overview of the different values that are found. If you want to know something more, we can take a look into the individual crack width check. This works exactly the same. We make sure the selection is set correctly and that all stages are used. And in this result, we find exactly the same value. Now, instead of a standard output, we can take a look into a detailed output again, and you can find the full overview of the crack width check. With this information, you can make sure you can evaluate your reinforcement and make the changes necessary to fulfill this check. You can change the reinforcement by selecting it and clicking on Edit Reinforcement. There we can select each reinforcement bar and change the amount of bars as well as the diameter of the bar. And right now we are changing the additional reinforcement which was added on the bottom in the middle of our beam and on the top at the end of our beam. After these changes are made, we can perform exactly the same check and we can review the results again. We will take a look into the crack width check again, and in this case we will see our modifications are taken into account and that for now the unity check is sufficient. Now, something to remark here as well is that you can take a look into the result of construction stage 1 as well, and in the detailed output you should find that the E modulus is modified based on that first stage because our material was only 7 days old. Here you can find another overview of the difference in the required reinforcement between a standard calculation and the construction stage analysis. Now that we have taken a look into this for a 2D model, we can do exactly the same for a 3D model. The basics here are the same. On the left, a standard linear analysis without construction stages. On the right, you find the model with construction stages. In this case, again, different stages are created for each different floor. Keep in mind that this is just an example of how you can use the construction stages. It is also possible to create different stages for columns and walls separately, and so on. Apart from these stages, we also apply the material modifications again to make sure that the age of the concrete is taken into account in each construction stage. Since this model is already calculated, we can start by taking a look into the results. We will first take a look into the 2D internal forces of one of our slabs, and then compare the standard results with the construction stage results. Once those are visible on screen, you will see that there is a different distribution and that it's mostly concentrated along the transfer beam that we find in this model. Other differences in the internal forces are less prominent. Similar to what we have done before, we can take a look into the reinforcement design as well. As we did for our 2D model, we can take a look into the reinforcement design of our 1D member, the transfer beam here again, and we see that the required reinforcement was more in the construction stage model. We can do the same for our 2D reinforcements. There we can as well take a look into our reinforcement design, and we start by taking a look into the required reinforcement. We choose direction 2+ right now, so it's the top side of our plate, and we see that there are some different results, mostly concentrated around the transfer beam. Other results will be quite similar. We can check the same for a different direction, for example, on the bottom side, and there we will see the same different results, mostly around that transfer beam. The difference you find in these results are mostly caused by the different E modulus that is used in the different stages, since a lower stiffness is used during the analysis. With the result table, you can then further take a more detailed look into the different results in all the different directions that you find here. Here you find another overview of the difference between the required reinforcement for the standard analysis and the construction stage analysis. Instead of checking the required reinforcement, we can then again take a look into the provided reinforcement. And here we start by taking a look into the unity check for this provided reinforcement. We see here that no red is found, so all unity checks are below 1. We can now also take a look into the configuration, which will show us what the diameter is chosen in the reinforcement template and the spacing in between. For direction 1-, I find diameter 16 with a spacing of 150 millimeters, and it seems to be the same in the other directions as well. Not only this provided reinforcement template is supported for 2D members with construction stages, also the user reinforcement can be taken into account. Let us add some lower and upper reinforcement to the full area of this slab with the command 2D reinforcement. You will have the possibility to take this user reinforcement further into account for the different checks. Let's overview the properties used. For this 2D reinforcement on the top and the bottom, both diameter 16 is added with a bar distance of 150 millimeters in all directions. So in general, the same as our provided reinforcement template. We start by taking a look into the punching design. Keep in mind that for 2D concrete checks, you need to select the type of reinforcement that needs to be taken into account during this check. Now we will use the defined user reinforcement, but you have the possibility to choose the required or the provided reinforcement as well. In this case, we see a green value is represented, which means that the check is satisfied and that no punching shear reinforcement is necessary. Next, we can also take a look into the crack width check. Here again, you need to modify the type of reinforcement to take into account. All the same options as discussed before will be available. With these results, you can immediately see where the concrete will be cracked and if the crack width is too large whenever a unity check higher than 1 is found. You can also take a look into the exact crack width size by changing the value you are looking into. In this case, for all locations, a crack width below 0.3 millimeters is found. The detailed report will again give you a full overview of the check and can help you to change the reinforcement design accordingly. Lastly, also the concrete to the bending check can be combined with the construction stages analysis. The only difference for this check is that only user reinforcement will be taken into account. The provided reinforcement template will not. This is the same for the standard linear calculation, so there is no difference there. This check takes the exact position of reinforcement into account and thus gives you the opportunity to check a member with one or multiple reinforcement layers. Apart from these visualized results, you can of course take a look again into the output of this check to find all the necessary information you need to modify anything. In the next topic, we will discuss the improvements done to the automatic generation of the 3D wind loads. In general, we now cover two new aspects. One is the method of overall force, which can be set into the national annex. The other one is friction loads on roofs. To take a look into both topics, we will go to an example with a canopy for which the load now is generated without those two improvements. First, we will take a look into the methods of the overall force. And you can modify this in the national annex. We can find it in the top. There you can open the annexes, and in topic 1.4 you can open your wind data. There we can change the coefficient type to the overall force. Now, once we regenerate the wind loads, this is taken into account and we should see the loads are modified. Let's take a look through our different load cases and you see right now that you get an overall force instead. The second improvement here are friction loads. These friction loads will be applied in the Y direction. Let's first take a look into our 3D wind, which is generated without these friction loads. Here you will then find the different surface loads as you would expect. To change anything to this friction load, you go to the properties of your load panel and click further onto the wind data, where you can activate the friction force. You can also choose the surface type, which is now set to smooth. Once you run the 3D wind generator again, you can take a further look into those forces and you find that for this wind load case, a friction load is added. If we now change the surface type to very rough, we should notice that its value of friction load gets much higher. The third topic of today will be the dynamic analysis, and we first take a look into the harmonic analysis. To make sure you can perform the harmonic analysis, we first need to check the active functionalities. We need to make sure that dynamics is toggled on, and on the right we need modal and harmonic analysis, which is by default activated once dynamics is selected. In this example, you will find two load cases. One is the self-weight and the other one is the foot traffic. Now, to start off, we will first perform the modal analysis. To do so, we first need to create some mass groups. Here, one is created for the self-weight and one is created which is linked to the foot traffic load case. Then secondly, we need to create a combination of mass groups as well. In here, the same masses as we just created are found. Now that we have those created, we can immediately perform the modal analysis. We will be able to take a look into those different modes that are calculated by using the 3D deformations. Instead of taking a look into the 3D deformations of a general load case, we will have the possibility instead to change the type of load to mass combination. In this mass combination, you can find the different modes that were calculated. We will take a look into the first, as we can see here, the second, and eventually the third as well. Of course, you can take a look into the other modes that were calculated. Now, let's say we would like to perform an harmonic analysis on this model. In that case, we need to create a different load case. We create a new load case, call it harmonic, and then we can change the load type from static to dynamic. Once this is changed, you can choose the specification, and here we have the possibility to choose harmonic, and then secondly, we can choose the method that will be used. We will use the modal superposition for now. Then right below that, you can choose the damping type. You have both Rayleigh damping and constant damping. What is the difference? If you select Rayleigh damping, then you will need to fill out some properties like the frequency and so on, and the damping itself will be calculated. Other than that, if you choose constant damping, then you fill out the value for that option. Let's use constant damping for now and take a look into the different properties here. Next up, you find the period division for summation, where you can choose different values. The default value will be 72. Eventually, we can also give a load signature. Now, imagine that the frequency used here would be 4 Hz. In that case, we will notice that our first mode, which was around 2 Hz, will not be influenced that much. Our third mode is closer to this frequency, so it could be that there we find more influence since our structure will resonate. To take this into account, we can add this load signature. Now to show you this, we will copy this existing load case and make sure we add this load signature. This will allow us to assign a specific mode to this harmonic load case. Let's first go to harmonic 1. There we activate the load signature and we make sure that the mode for load signature is 2. The effective load direction will be the z-axis. For harmonic 2, we do the same. For that case, we choose the third mode. Other settings are exactly the same. The loads will then be displaced following this signature that is assigned. Now that these load cases are created, we still need to add some loads to these load cases. The loads you add here will be the same as the load from our footbridge. So in this case, for the harmonic load case, we will add a surface load to the same area with exactly the same value. We will do the same for harmonic 1 and 2. And there we are. We do the exact same for harmonic 2. And lastly, for harmonic 3. Now that everything is added to our model, we can run the analysis. During this analysis, you will notice that the harmonic load cases are calculated parallel from each other, so not separately as was the case before. Now, when we take a look into the results, we will take a look into the displacements again, and we start with our general load case of the foot traffic. In this case, we find a value which is around 46 millimeters. If we now take a further look into our harmonic load case, we find a first displacement of 15 millimeters. Now for this load case, no load signature was assigned. For harmonic 1, we did assign a load signature, and there we find a displacement of 31 millimeters. Lastly, for harmonic 2, we assigned a load signature as well, and there we find a displacement of 40.7 millimeters. If we now go back to our load cases, we can now say that this load signature gives you the possibility of creating a combination following the mode that is indicated. This means that we can recreate the same result by defining this load case differently. First of all, we create a copy of this load case and we will toggle off the load signature. To make sure that we then find the exact same result as what we have seen here right now, we will make sure that we change the loads that are created, especially the direction in which the loads are working. So harmonic 3 is exactly the same as harmonic 2, but we will change the loads specifically by creating 3 loads in the direction of the mode that we found before. So first we create our 3 loads, and I will change the sign of the first 3 loads to make sure it works the other way around. There we are, we run the analysis again, and now we should see that the results will be exactly the same for this third harmonic load case. So for our second, we find 40.7, and for our third, we find exactly the same results. So this load signature makes sure that you apply the right direction based off those modes. We can also take a look into what would be a dangerous result. For example, we change the frequency from 4 to 3.5, which is pretty close to the mode that we found. If we then would take a look into our result, we expect our deformation to be much larger because the structure will be resonating. Let's take a look there. If we now take a look into the same deformation of our harmonic 2 load case, we find a deformation of 165 millimeters, which is for now the most dangerous situation. Next up, we can take a look into a new feature, which is the vibration analysis. That is also a functionality you need to toggle on before you can use it. To start off, we go back to our load cases and we will change a property here. Right now we use the specification harmonic and we will change it now from harmonic to harmonic range. By doing so, you will now have the possibility to define a specific range with a minimum and a maximum value. The third value you define is the step in between, which is used to go through this range. So we will use 0.1 for now. The rest of the steps are exactly the same. I perform the analysis and you will now see that for my harmonic load cases, now all the different frequencies are calculated. Now, before we take a look into the results, we are going to make a result class to make sure that we have different classes for our different harmonic load cases. So I have one for my first load case, then the second one, and then lastly for harmonic 2 as well. Now we can take a look into the deformations, but instead of taking a look into each load case separately, we will go to these classes to take a look into these results. And now we get a full overview of the most extreme results of this frequency range. And for this H2, we find now the same range or the same displacement that we found before, which is around 166 millimeters. Other than these displacements, we can also take a look into detailed dynamics results. And here you first select the right result case, which can be a load case or a mass combination, and below that you find the values to choose from. In this case, we will take a look into one of our harmonic load cases. So we change the type of load to load case. For these type of load cases, you will find different type of values. You find the displacement, velocity, and acceleration. Let's take a look in one of our harmonic load cases. Let's choose harmonic 1.3.1. And we first start with the displacements. Now we are taking a look into the X direction. Let's change this to the Z direction. Then you find the displacements of these nodes. Next up, we can take a look into the velocities or the accelerations. Here you can find a comparison between the linear analysis, the harmonic analysis, and the harmonic range analysis. It's really important to highlight that when you modify the structure, the harmonic range allows you to cover the possibility of resonance for your structure, since any modification of the structure can influence the found period. The last topic that we will discuss today is the new development related to the interoperability with freeload tools. We are talking about the B5 Plus module. To find a freeload module, you can use the SCIA spotlight on top to search for it. And in this case, we were searching for the freeload reinforced column tool. If you want to add it to one of your menus on the bottom, you can always drag and drop the icon. To export a column to this tool, we can select it and we can use the tool to export it to the B5 Plus tool of freeload. In here, you can either design the reinforcement of your column or perform a fire check. Now let's first take a small look into this project here. We should be able to find the boundary condition as the support here, and we will also find the different imported loads from SCIA Engineer if we go to loading. There we can now find the permanent loads and so on, which were imported from SCIA Engineer. Now we can perform the design. We can check the calculation mode, which will either be design or check, and we can activate the fire design based on STEM or on the code. Now we choose a class of fire resistance. Let's choose R60. We can choose the calculation mode here. And then next up, we will be able to choose some settings here. The settings you find here are all related to this check. You can find the fire resistance here again, as well as thermal addition, inclination, and so on. If we then take a look into the reinforcement options, we can do three things here. We can manually design reinforcement, we can create reinforcement, and we can remove existing reinforcement. We will later on see how to add reinforcement manually. On the bottom there, you will also see that there is an export to Allplan already, and there you can see that we continue to improve the interoperability between our software tools. So now from Freelo, you can already export something to Allplan. There are also some settings you can change for your output and results that you can set before running the calculation. You can either choose to take the first order into account, second order, and so on. Once those are set, you can calculate your model and it will propose a design to us. In this case, we see the design contains 4 bars of 14 millimeters, and you can choose to increase when necessary and run the calculation again. Next up, we find the temperature analysis, where you can still change some properties, and once those are changed, you can run calculate. Then the full calculation is performed and the results should be found. On the bottom right, you now already get an overview of the designed longitudinal reinforcement and if it is sufficient. And in this case, we see that for the fire design, this is not sufficient. To take a further look, we can also take a look into the document where you can find a detailed output of these results. This is a live output, so it will immediately be modified when you make any changes. Now in here you get a detailed overview of the different internal efforts and so on, and you can find here in this case that the reinforcement is insufficient as well. Other than this document, you can also find a graphical output that you can find on top in the tab results, and there you can find the different internal efforts and so on. You can check the deformation, the reinforcement, all the options are there on top. Now we can also choose to manually add some reinforcement here, as stated before, to change the amount of reinforcement that is used. Let's take a look into that menu specifically, and we can choose here what arrangement we can use for the reinforcement. So let's choose a template here, which we know will cover the amount of necessary reinforcement. Now, when this is changed, you will need to recalculate to take everything into account, and then we can see if our reinforcement is sufficient or not. So let's run the calculation again, the same as before. Take a look in our temperature analysis. And then afterwards, we see now that our required reinforcement is fulfilled, that the reinforcement we applied is sufficient. On this note, we can end the demonstration of the new features in SCIA Engineer version 25. I hope you find it interesting, and if you have any questions, do not hesitate to reach out. I will now give the word back to Michele.
That was an impressive demonstration, Merit. Thanks a lot for showing us the capabilities of this version SCIA Engineer 25. Now we have already some questions. Please continue to ask your question in our chat, and we will ask one of those to Bjorn. Bjorn, can freeload be used in combination with an harmonic analysis?
Yes, that can be used. In the past, it was only possible to use nodal loads, but now with the new development, it is possible to use both nodal loads, line loads, and even surface loads in a harmonic load case.
Thanks a lot, Bjorn. And now we continue with our program. We have now Nigel, who will show us Beam Plus and autoconverter.
Hello everyone, and thank you for joining me today. I will speak about some innovation called autoconverter that we have developed at Allplan to ensure that engineers are able to effectively and efficiently create structural models from 3D physical geometry that is created in authoring tools such as Allplan and SDS2, for example. So my name is Nigel Rees, and I represent the Cloud Service Division here at Allplan. Within the Cloud Services Division, we are really responsible for adding value around our desktop products throughout the whole Allplan group of products, where one of those areas is automation of processes and integrated workflows. Also, we have many of these workflows spanning multiple disciplines. So this is no different for autoconverter. An autoconverter really is the key to presenting an open BIM workflows with structural engineers in mind. So in this short session, we will take a look at how we link a geometrical 3D model to a structural model, and a short number of steps required to do this, and then investigate some of the benefits of doing this. We will look at how the system is hosted, how we utilize the autoconverter functionality to create the analytical model, and how we connect this with multiple other software programs. Autoconverter is our function for developing the analytical models, and this is hosted on our cloud-based model management platform called BIM+. Important to remember, we are showing a workflow here that has many advantages for the structural engineer, one of which is creating an analytical model quickly, but also all the features of a collaborative model management platform are also exposed to the user. BIM+ works as an independent collaborative environment that is able to accept data from any authoring tool at any point in the creation process, which means we are able to bring models together in a federated model environment. One of the added benefits of having services built around the BIM+ data environment then means that these services can be used with the data contained in that environment. Great news for autoconverter, as this means that model data that comes from Allplan or SDS2 or any other authoring system can be used to construct an analytical model for structural analysis. Of course, the natural benefits of collaboration can also be achieved. So real-time collaboration by project stakeholders who are able to see the model history, investigate any changes through multiple revisions of the model, and report back on those changes. The creation of issues through our issue management function is also highly valuable, allowing the engineers, architects, and 3D modelers to understand where problems lie within a set of models and assign responsibility to manage the change. Within BIM+, we offer a very robust data environment that can be used, as I mentioned before, across many disciplines to connect data, efficiently manage that data, enhance communication, and build effective workflows to aid productivity, and to help us reach the goal of digital delivery for our projects, including all disciplines involved. Further to that, we are able to bring quite advanced workflows on both the physical model representations that we host within BIM+, the analytical structural models, and bring in 2D documentation to support the derivation of a complete project model. We are able to represent drawing data within the 3D model environment for better understanding the status of the model against the drawings to be issued, as well as any clashes within the model that can be reported on, and then also an approval process which can be invoked to assign further responsibility within the team to approve any model changes. So we have complete visibility then on the process for the managed model. So let's take a little look at the autoconverter functionality that we've developed to aid the process of engineers from taking that 3D geometry model into a structural analysis model. So principally, autoconverter combines the 3D modeling process with structural analysis software. So if you are using Allplan for modeling, for example, and would like to have a managed environment for developing analysis models in SCIA, for example, then this is a great option, a great environment to do that. Of course, then having it sitting within a hosted collaborative environment manages that process. It's a controlled environment for everyone involved. And one of the principal advantages of autoconverter is that it is entirely flexible to the needs of the engineer. It's an intelligent system that can recognize multiple formats. Of course, if there is a direct link to autoconverter, such as we have with Allplan, it's a fairly straightforward process to build an analytical model from the resulting data. But we do not limit ourselves to just this data. It's also possible for engineers to bring in IFC files directly into that process, either to so we can work in isolation on IFC files, or to bring IFC files in communication with models that have been directly brought in from other processes. So autoconverter clearly guides the engineer through a series of processes to derive a structural model, intelligently mapping cross-sections, materials, etc., as you go from one end to the next. Here at Allplan, we also developed a file format called SAF, so the structural analysis file format. So this provides a description of the model created in a human-readable format from within Excel. This is incredibly important. So as well as being human-readable, it also allows the engineer to make edits manually and bring those edits back into the managed workflow. SAF is well supported within a wide community of engineering structural analysis software, including both Freelo and SCIA. So now we can take a look at autoconverter in a bit more detail. So here we see the managed environment that we were that I was describing earlier. So the model can often exist in the BIM Plus environment, providing the user with, as mentioned before, the many tool sets available within this collaborative project. It's important as well for the engineer to be able to assess early on the validity of the model, check the dimensions, and also interrogate the object properties within that model before anything is sent to autoconverter for further processing. So of course in BIM Plus it's also possible to edit properties, to update the attributes and perform a task commonly known as attribute management, but also to attach reports alongside the objects. So whether that is design data or drawing data, we can put any amount of attachments alongside the structural or the architectural information contained within that model. And again, as stated, if there are issues that we need to flag up to anyone else in the team, we're able to do that and then set the required responsibility and the due date for those issues to be resolved. So then when we move that model into the autoconverter environment, we have a number of steps that we need to follow in order to create a successful representation of the model for structural analysis. So that is essentially in the first mode, we need to clean up the model. So we need to take anything out of that model that doesn't really conform to a structural element, such as grid objects that may come along from axis definition when creating a model, and anything that we feel is not required for structural analysis. That may be a pure architectural item that's not defined as potentially a load-bearing object. And then once we've done that, we of course can set up a bunch of filters that allow us to make that cleanup process easier in the future. And then once we've cleaned up that model, we're not deleting any objects. They just get removed from the process, and we can see that they already still exist within that model. So on the first pass of recognizing the objects, the autoconverter will now make an assumption and recognize the objects as either 1D elements and assign a type. So whether it assumes the objects to be beam or column, of course you're able to go in and change that. But autoconverter now needs to establish what the section geometry is and what the materials are. So the first pass on actually creating that analytical model is to do something called go through the recognition phase. So we recognize the model. So there's nothing joined at the joints there. So it's not a complete structural representation, but at least now the cross-sectional geometry is recognized. The materials are now mapped across the databases, and it understands what type of model it is. Now the next job is to say, okay, I need to join this model together so that I get that continuity across the frame and across the surface elements, so that I can run this model successfully within the structural analysis tool. So that we call alignment. And once we've done that and gone through the various options, we can see that we're presented back with a good model with continuity across all the interfaces, slabs and walls joined together, beams and columns joined together. So we're safe in the context that we can now send that model across into a structural analysis tool, in this case SCIA. But we can also export that representation of the analytical model back to our host environment BIM+, so it becomes part of the project environment. So we can effectively now start to make the history of that model straight away. So then, of course, we want to analyze this. So at this point, we now switch across to our structural analysis tool, in this case SCIA, which is SCIA and Freelo can be used at length with the integration with autoconverter. But now what we're going to do is retrieve the model that we've saved back into BIM+ and bring that directly into the SCIA analysis tool. So we're creating that association between the two platforms. So that means that whatever we do within SCIA, any changes that we make, we can represent those changes and go through those approval processes within BIM+, so everyone can look and review. So within this process, we see that autoconverter is a really good step towards transferring models from Allplan or multiple other CAD applications to SCIA Engineer. It only takes a few steps to create the finished analysis model. And you save a lot of time when creating analysis models and therefore more time for calculation. I think it's also important that we can build up a set of different models. So if you need to do some testing and build a model in AutoConverter that's representative of a linear static model, we can build that and archive that back in the BIM Plus environment for further usage. And we can also create a different model for dynamic types of analysis, where we might put more offsets in there or different loading types and that sort of thing, and build that into our revision process as well. So that's it, a very short overview of AutoConverter and how it plays a part in the development of structural analysis files within SCIA Engineer. Thank you very much for your attention, and have a nice day.
Thanks, Nigel, for the informative presentation on BIM Plus and AutoConverter. We are now moving into our Q&A session. We have our SCIA expert here ready to answer all your questions from the live chat. The first question: can the loads be applied according to a specific modal shape in a harmonic analysis?
Yeah, that's the one that I can answer. Indeed, you can first run a modal analysis to find out your modal shapes, and then afterwards you can assign a specific modal shape to your harmonic analysis.
Thanks a lot, Bjorn. Second question. There is a question about learning material on construction stages, design and checks. What is already available for our engineers? I think you can answer also this one.
Yeah, definitely. First of all, online we already have some documentation about construction stages, and that's available on our web help. So that's help.scia.net. And there you can find already a lot of information on the functionality, but also you can read about which checks and which materials are supported. Besides that, there's also a webinar planned. It will be a topic on the application of construction stages on a multi-story building. So keep an eye on our website and newsletters for that.
Thanks a lot. I'm looking forward to also look at that.
Okay.
And now we have another question. We saw Nigel's presentation about AutoConverter and BIM Plus. This is one of the steps we took after the merge with Allplan. What are your thoughts, Gino, about this?
Well, I'm very excited about that, about the synergy and collaboration functionality between our products. This is something that allows the users to have additional design possibilities. So, very good.
Thanks a lot, Gino. Before we close, is there anything that you want to add, Bjorn?
Yes, I think it's very nice to see that the product and also the development team are very aware of the questions that arrive from US customers to our support team. And for example, we saw a lot of questions about harmonic analysis, and especially about the velocities that are were not available yet as output. And now with the new harmonic loadings, the velocities will be available as output, which means that you can ask for them when you design, for example, a footbridge. That's very nice.
Thanks a lot. That's really interesting. So all the other questions will be answered directly from our expert in the chat, or we will come back to you later on. As we come to an end of our conference, I'd like to take a moment to thank you all for your active participation and engagement. Your questions and comments have made this much more insightful. I hope that today's presentation and discussion have given you a deeper understanding of how SCIA is committing to unifying precision and performance. Our aim is to give you to provide you with tools that are precise, efficient, and high-performing. And we hope that you found this conference beneficial in understanding how we want and we are committed to achieve that. A special thanks to our speakers today, so Jad, Marco, Merit, and Nigel, for their informative and insightful presentation. And of course, our SCIA experts that are always available to accompany you to the question of today and of tomorrow. Should you have any further queries or require more information, please don't hesitate to contact us. We are always here to help. Thank you again for joining us today. We look forward to seeing you in our future events. Until then, take care.